Let's now think about planets. Planets go around the sun. There's no string. So who is pushing? Who is pulling? Well, it's clear that it must be gravity. It must be the sun that is pulling on the planets. Now I realize that the orbits of planets are not nicely circular, so it's not really a uniform circular motion. We will deal with orbits in great detail in a few weeks, circular orbits and elliptical orbits. Let us just assume for simplicity now that the orbits are roughly circular, just to get a little bit of feeling for it. And you can look up now in your book, which I did for you, even in your preliminary version, you can look up what the mean distance of the planets is to the sun, and you can look up what the period is, the time to go around the sun. The time to go around the sun is not the same for all planets. The planets are not attached to a turntable. Anywhere, any person on a turntable would go around in the same amount of time. We know that that's not true for planets. It takes the Earth a year to go around. The Sun, it takes Jupiter 12 years to go around. So don't make the mistake to think that omega is the same for all planets. That's not true. So I look up the distance, the mean distance to these various planets, and you see that here in millions of kilometers. Notice that Mercury is about 100 times closer than Pluto. By the way, this is on the web, so don't copy this. You will find this on the 801 homepage. Then I looked up how many years it takes to go around the Sun. 12 years for Jupiter, 1 year for the Earth, and I looked up all the other values. Then, since I know the periods, I can calculate omega. Omega is 2 pi divided by t, so I know omega. And then I take omega squared times the mean distance to the Sun, and this is, of course, the centripetal acceleration. So the planets experience this centripetal acceleration in some crazy units, but who cares about the units here? And notice that Mercury, which is 100 times closer than Pluto, has a centripetal acceleration which is 10,000 times larger than Pluto. 100 times closer, has a 10,000 times larger centripetal acceleration. So what I did was, I plotted this data, the centripetal acceleration versus the mean distance to the Sun, and I did that on log paper. And what immediately is very striking is that all these points, I've done them for all the planets, they fall on a straight line. And so, what is the slope of that line? Well, I tried various slopes, and I found that the slope is very, very close to -2. Here is a slope of -2, and I can overlay this and notice that the fit is absolutely stunning. Therefore, you cannot escape the conclusion that the centripetal acceleration, which is the result of gravity, falls off as 1 over r squared. We refer to this often in physics as the 1 over r square law, and therefore the effect of gravity itself must go down with r squared. So if you are 100 times further away, like Pluto compared to Mercury, then the centripetal acceleration, which is due to gravity, is 10,000 times smaller. And we will learn a lot about gravity in the future. We will just leave it for now. If you took the Sun away, it would be like cutting the string that provides the pull, and in that case, what you would see is that the planets would just take off along a straight line. They would continue to go. They wouldn't have anything to pull on them anymore.